Quantum entanglement is an amazing phenomenon that goes beyond classical physics. However, many people do not really understand this, because our thinking follows classical physics. Using 3D animation, I will unravel the secrets of the quantum entanglement in the polarization of photons. This shows linearly polarized photons. The arrows indicate the polarization angle. If the polarization angle of the photon matches the polarization filter angle, 100% of the photon will pass through the filter. Tilt the filter 90 degrees and all photons will be blocked by the filter. If the filter angle is 45 degrees, 50% of the photons will pass through and the polarization angle will be the same 45 degrees. If the filter angle is set to 22.5 degrees, which is 1/4 of 90 degrees, about 85% of the photons pass through the filter. If the filter angle is set to 67.5 degrees, which is 3/4 of 90 degrees, only about 15% of the photons pass through the filter. This relationship is shown in the graph. The passage rate is not proportional to the angular difference and is represented by a cosine squared curve. This curve can be derived from the theory of electric field vectors. Light is a spatial oscillation of the electromagnetic field. For linearly polarized photons, the electric field oscillates in only one direction. A polarizing filter only passes through light components which vibrate in the filter direction and reflects or absorbs all orthogonal components. Let's consider the case where the linearly polarized light is tilted by theta degrees. Due to the vector nature, the magnitude of the electric field vector becomes cosine theta times larger. When the voltage increases by a factor of cosine theta, the current also increases by a factor of cosine theta. Brightness is calculated by voltage x current, so it is cosine squared theta. Since brightness is proportional to the number of photons, the passage rate will also be cosine squared theta. Next, I'll show you what happens with unpolarized photons. As an example, sunlight is unpolarized. Unpolarized light can be considered to be a superposition of light in all polarization angles. When the photon hits a polarizing filter, this superposition state collapses and changes to linear polarization in the filter angle. Although the waveform is random, the direction of the electric field is limited to a single plane. And we can show this as an animation of each photon. The semi-transparent disks represent the random polarization angles. This unpolarized state collapses when the photon hits the polarizing filter, and 50% of the photons pass through the filter. One important point is that the probability of passage is 50% for any filter angle. Next, install a second polarizing filter on side A. An unpolarized photon will pass the first filter with a 50% chance and pass through the second filter as a linearly polarized photon. In this case, if the angle between the two filters is theta, the probability of passing through the second filter is cosine squared theta. Now that we're prepared, Let's move on to explaining quantum entanglement of photon pairs. What we are showing you is an animation of photons based on the strong Copenhagen interpretation, which is currently the mainstream. A pair of entangled photons is simultaneously output from emitter A and emitter B. The purple spiral represents the quantum entanglement. Entangled photons are always unpolarized. When a photon hits the polarizing filter on side A, its polarization state is collapsed and it passes through the filter with a 50% probability. In the Copenhagen interpretation, when a photon on side A collapses, the entangled photon on side B also collapses. The polarization angle of the photon on side B will be the same as the filter on side A if the photon passes on side A, and will be perpendicular to the filter on side A if the photon is blocked on side A. However, it is just an interpretation, and you cannot visually confirm the collapse of photons on the B side as shown in the last animation. What can actually be observed is the pass-block result obtained on side B by passing the photon through the installed filter. A pair of photons that pass the A side filter will pass the B side filter with 100% probability. A pair of photons blocked by the filter on side A will always be blocked on side B as well. So why do we think that such photon collapse occurs in the Copenhagen interpretation? This is because the photon passage rate is cosine squared of the angle between the filters, just like when a second filter is placed on side A. If this is the case, we can only assume that the B-side photon has already collapsed to the same linear polarization as the A-side photon. However, Einstein had serious doubts about this phenomenon in which the collapse of the polarization angle of the photon on side A appears to be transmitted instantly to side B. The two filters can be separated by tens of thousands of light years. Even so, the polarization angle is immediately transmitted to the other photon, and the assumptions of the theory of relativity seem to be broken. Einstein called this hypothetical information transmission faster than the speed of light, spooky action at a distance. However, during his lifetime, any experimental verification of this strange action could not be realized. But Einstein was aware that the quantum equations contained this strange action, and he suspected that quantum mechanics was still incomplete. At the same time, Einstein also suspected the indeterminacy of the polarization angle of unpolarized photons. In fact, he believed that the behavior of photons when they are collapsed by a filter is determined in advance, but we simply do not know yet the laws behind this. Below, we will look at two classical physical models that appear to be able to explain quantum entanglement, and assume the deterministic physical model Einstein believed in. The first classical physical model assumes that unpolarized photons have polarization angle information as an internal parameter. In this animation, the hidden internal angle is shown by an arrow inside the transparent disk. Polarizing filters have an internal blocker that passes only photons with internal angles within a range of plus or minus 45 degrees from the polarization angle. We also assume that the internal polarization angle of each entangled photon pair is the same. Then, for example, if the polarizing filters on sides A and B are at the same angle, The paths blocks of the entangled photon pairs will be perfectly consistent. This matches the results of the actual experiment. Also, if you tilt the filter on the B side by 90 degrees, the blocker holes will no longer overlap, so no photon pairs will pass through A and B at the same time. Setting the angle of the filter on side B to 45 degrees halves the area of overlap of the holes, so that 50% of the photon pairs pass through both filters. Furthermore, even if the filters on sides A and B are rotated by the same angle, the overlap of the blocker holes is the same, so the transmission rate does not change. Unfortunately, this is the last point where this model agrees with experiment. For example, if the angle between the filters is 22.5 degrees in this model, the overlap area of the two blocker holes is 75%, so the passage rate will be 75%. But in case of entangled photons, the probability of passage is a cosine squared, so the matching rate of the passing photons must be about 85%. In fact, in this classical model, the coincidence rate between photons is always proportional to the angular difference between the filters, which is inconsistent with quantum entanglement. If this is the case, by thinking the other way around, would it be possible to explain the quantum entanglement making the probability of passage be cosine squared? In this second classical model, the polarization direction of both photons is aligned along the x-axis or y-axis and output alternately from both emitters. If both polarizing filters are aligned along the y-axis, then any photon pair aligned along the y-axis will pass both filters. Also, if the filter on the A side is aligned along the y-axis and the filter on the B side has an angle of theta from the y-axis, the cosine square of the angle is the coincidence rate of photons that pass. This passing probability perfectly matches the entangled photon pair. So, is there a classical physical model that can explain the quantum entanglement as Einstein predicted? For a further confirmation, let's rotate the filters on both sides and align them at 45 degrees from the y-axis. In this setting, because the photons are polarized along either the y or x-axis, when they pass through a 45 degrees filter, 50% will pass and 50% will be blocked. However, there is no way to synchronize the pass or block of photons on both sides. Therefore, the pass-block rate of photons cannot match perfectly between sides A and B. This is different from the results of quantum entanglement experiments. The quantum entanglement model requires angular isotropy, but the second classical physics model does not satisfy this requirement. In 1964, physicist John Stewart Bell from Northern Ireland devised an inequality to determine whether the quantum entanglement fits within the framework of classical physics. In the following, we will explain the Wigner-D'Espagna inequality, which is an inequality that looks different but has the same meaning as the Bell's inequality. In the first classical physics model, let's place filters on sides A and B at 0 degrees, 22.5 degrees, and 45 degrees from the y-axis. In this case, the probability that one photon passes the filter and the other is blocked by the other filter is used to evaluate the probability. In the first example, if the filter on side A is set to 0 degrees and the filter on side B is set to 22.5 degrees, the area of photons that pass side A and are blocked by side B will be the green part in the diagram on the right. The total angle of the photons entering the filter is 180 degrees, so in this classical model the probability is 22.5 divided by 180 equals 12.5%. If we call the 0-degree filter pass alpha and the 22.5-degree filter pass beta, then this probability is written as p alpha intersection beta bar. Also, if you set the filter on side A to 22.5 degrees and the filter on side B to 45 degrees, the angle difference is still 22.5 degrees, so the probability is the same 12.5%. If we write the 45-degree filter pass as gamma, then this probability becomes p beta intersection gamma bar. Finally, if the filter on side A is at 0 degrees and side B is at 45 degrees, the difference in angle is 45 degrees, so the probability is 25%. Let's put these together on one diagram. In this case, the probability when the angle difference is 45 degrees should be equal to the sum of the probabilities when the angle difference is 22.5 degrees. This is actually Bell's inequality. But this isn't an inequality. Let's consider the case this equality becomes an inequality within the scope of the classical physical model. In fact, for versatility, the first classical model was said to be isotropic with respect to the filter angle. However, since Bell's inequality only uses 3 angles, it is not necessary for all angles to have the same properties. For this reason, we must also consider the case where the filter setting angle and the blocker angle do not match. Now consider the case where the angles of the alpha and gamma blockers are fixed, but the angle of the beta blocker varies. In this case, if we assume that the photon has an internal parameter other than the polarization angle, it is possible to alter the blocker angle only when the filter is around 22.5 degrees. In this classical physics model, if the angle of the beta blocker overtakes the angles of the alpha and gamma blockers, the sum of the probabilities on the left side becomes greater than the right side, and the equality sign changes to the inequality sign. Though in quantum entanglement, the probability that a photon passes through side A and the other is blocked in side B is half the value of subtracting the cosine squared angle difference from 100%. Hence, p alpha intersection beta bar equals 7.5%. P beta intersection gamma bar equals 7.5%. P alpha intersection gamma bar equals 25%. In this case, the sum of the probabilities on the left side is smaller than the right side, so we know that Bell's inequality is violated. Now, some of you may be looking at this diagram and thinking, wait a minute. You may think it is possible to lower the probability of 2 narrow regions. That is when the photon side also has a certain blocking radius. In this model, the probability of passing through is smaller when passing through narrower area. Therefore, the sum of the probabilities of 2 narrow regions is to be smaller than the overall probability. However, in reality, this model does not work. This is because in Bell's inequality, one term in the brackets is a blocking condition represented by a bar. As shown in this animation, the angle of the block condition is expanded rather than shrinked. In this Bell's inequality, one term has a bar, so the opposite inequality does not hold within the scope of classical physics. Actually, Bell himself, like Einstein, seems to have thought that this inequality would never be broken. Later, Alan Aspect and his colleagues discovered the violation of Bell's inequality through quantum entanglement experiments of photons, and were awarded the 2022 Nobel Prize in Physics. This proves that spooky action at a distance does exist in the quantum world. Now, here's a question. If the filter angles are set to 0 degrees, 45 degrees, and 90 degrees, is Bell's inequality violated? While the relationship between the filter angle difference and the probability of passage is cosine squared, it takes proportional values at these angles. So it is not possible to violate Bell's inequality. However, the commonly cited case where one photon passes through a filter and the other photon also passes, and one is blocked and the other is blocked, is this angular condition. But under this condition, quantum entanglement is within the scope of classical physics. It may be no wonder that Einstein and Bell also misunderstood that quantum entanglement should be expressed by a classical physical model with hidden variables. Then, can we actually use quantum entanglement to instantaneously send the filter angle information on side A to side B? Again, I'm showing you the imaginary animation based on the strong Copenhagen interpretation. If you know whether a photon on the A side passes or is blocked, you can calculate the angular difference between the filters by summing up the passage probabilities in each case on the B side. However, if the passage of photons on side A is completely random, it is not possible to separately count the passage probabilities of photons on side B. As a result, side B can only obtain a 50% pass probability, which is the average of 85% and 15%. Since the brightness of unpolarized photons is always halved when passing through a polarizing filter, no information from side A is obtained on side B. However, Einstein also doubted the randomness of the photon passage. If there is a law here, and side B can predict the passage of photons at side A, then information will be transmitted from side A to side B at a speed that exceeds the speed of light. Fortunately, even today, the collapse of quantum states is thought to be completely random. Spooky action at a distance was proven, but the assumptions of the theory of relativity were not overturned. That's all I prepared by now. Were you able to clear your mind? When we try to understand quantum mechanics, we can realize how our understanding is bound by classical physics. For example, when you look at an animation based on the Copenhagen interpretation, it seems like communication faster than the speed of light is possible. It seems like we can control the entangled world instantly too. However, we cannot control the collapse of the wave function on our side, so we never be able to control the world on the other side through the entanglement. Einstein said, "God does not play dice, but in reality, God's rolling of dice made it possible for quantum entanglement to survive in the 4D spacetime in a manner consistent with the speed of light." Then, was Einstein wrong? Probably not. Quantum mechanics could be incomplete, because the world may be crafted as such. See you in the next video. This is Nomnom.